Welcome to this lecture on the beta distribution. Imagine you are looking at a new restaurant's rating on a food delivery app. It has a perfect rating, but you notice the score is based on exactly one review. Would you trust that perfect score as much as a slightly lower rating based on thousands of reviews? Probably not. Today, we will explore how the beta distribution helps us mathematically model exactly this kind of uncertainty. Now that we understand the need to model uncertainty, let us look at what the beta distribution actually is. In statistics, a continuous probability distribution is a curve showing the likelihood of a variable taking on any value within a range. The beta distribution is strictly confined to the interval between 0 and 1. Because it is locked in this range, it is the perfect mathematical model for things naturally bounded by those numbers, like conversion rates or batting averages. Its shape is controlled by two parameters, alpha and beta, representing observed successes and failures. As these change, the curve morphs, making it incredibly flexible. To draw this flexible curve, we use its probability density function. Conceptually, this formula takes our observed successes and failures and translates them into the height of the curve at any given probability. Let us break down the symbols. The variable x represents the unknown probability we are trying to estimate. Alpha represents our successes, pulling the curve higher when we have many. Beta represents our failures, pulling the curve lower when they dominate. Finally, the denominator is the beta function. This acts as a normalizing constant, scaling the curve so the total area underneath always equals exactly 1, which is required for all valid probability distributions. Let us visualize what this mathematical function actually looks like. Here you see a graph with the probability x on the horizontal axis, ranging from 0 to 1, and the density on the vertical axis. Notice how the shape changes based on our parameters. When beta or failures is higher than alpha, the curve peaks towards the left, near 0. When alpha and beta are equal, we get a beautiful symmetric bell shape in the middle. And when alpha or successes dominates, the peak shifts to the right, closer to 1. This diagram perfectly illustrates how the beta distribution adapts to reflect the evidence we have collected. Just like any dataset, this distribution has a center and a spread. The center is the mean, denoted by mu. Conceptually, it is incredibly intuitive. It is simply the number of successes divided by the total number of observations. This gives us the expected probability over the long run. The spread is measured by the variance, denoted by sigma squared. While the formula looks complex, notice the alpha plus beta terms in the denominator. As we gather more data, this denominator gets very large, causing the overall variance to shrink. Physically, this means the more evidence we collect, the less uncertainty we have, and our probability curve becomes much narrower. While the mean tells us the average expectation, we often want to know the single most likely value. In statistics, the highest peak of a distribution is called the mode. For the beta distribution, the mode represents the specific probability that has the highest chance of being the true probability, given our data. We calculate it using this formula, denoted by m. It is important to note that this specific formula only works when both alpha and beta are strictly greater than 1. It slightly shifts the peak away from the mean depending on the skew of the data. Before we move on, let us see this with a concrete example. Suppose a factory produces microchips, and historical data gives us a beta distribution with shape parameters alpha equals 4 and beta equals 12. We are asked to find the expected value, or mean, and the most likely value, or mode. First, we calculate the mean. We choose the mean formula because it gives us the long-run expected defect rate. We substitute 4 for alpha and 12 for beta. Adding the denominator gives us a total equivalent sample size of 16. Simplifying the fraction, we get 0.25. This means the expected defect rate is 25%. Continuing with our microchip factory, let us now find the mode, which is the single most likely defect rate. We can safely use the mode formula because both our parameters, 4 and 12, are strictly greater than 1. We substitute our values into the numerator and denominator. Performing the subtraction on top gives us 3, and the arithmetic on the bottom gives us 14. Dividing 3 by 14 gives a decimal value of approximately 0.214. So, the most likely defect rate is 21.4%. Notice this is slightly lower than the mean because the long tail of our skewed curve pulls the average up. Now that we have used these formulas, let us consider a special scenario. What happens when we have absolutely no prior information? Suppose we have not observed any successes or failures yet. In the mathematics of the beta distribution, we represent this state of total ignorance by setting both alpha and beta to 1. This might seem counterintuitive, but setting the parameters to 1 creates a completely flat line. This means that before we collect any data, we assume every single probability between 0 and 1 is equally likely. Let us prove mathematically why this happens. We are setting out to prove that a beta distribution with parameters of 1 is exactly the same as a uniform distribution. We start by taking our standard probability density function and substituting the value of 1 for both the alpha and beta parameters in the exponents. The mathematical reasoning here is straightforward substitution to see exactly how the curve behaves under these specific boundary conditions. Next, we simplify the subtraction in the exponents. 1 minus 1 is 0, which leaves us with x to the power of 0 and 1 minus x to the power of 0 in the numerator. This algebraic step sets us up perfectly for the final simplification to reveal the true shape of the distribution. Continuing our derivation, we apply a fundamental rule of algebra. Any non-zero number raised to the power of 0 is exactly 1. Therefore, both terms in our numerator simply become 1. Furthermore, the beta function in the denominator, evaluated at 1 and 1, also equals exactly 1. Substituting these simplified values leaves us with a simple fraction of 1 over 1. The final result is a constant value of 1 for any input x. We have successfully proven that this forms a flat horizontal line, known as the continuous uniform distribution. It perfectly represents a blank slate before any data is collected. So we have proven that a flat line represents total ignorance. This brings us to the true superpower of the beta distribution, how easily it updates when we get new information. This process is called Bayesian inference, which is a formal way of saying we are updating our beliefs based on new evidence. In this framework, your initial belief is called the prior distribution. When you observe new data, you combine it with your prior to form an updated belief called the posterior distribution. Because the beta distribution pairs perfectly with binary success or failure data, the math for this update is incredibly simple and elegant. Let us look at the formulas that make this updating process so simple. Conceptually, you do not need complex calculus to update your model. You just add the counts together. Alpha prime represents our new updated shape parameter for successes. We simply take our prior parameter alpha and add the number of newly observed successes, denoted by S. Similarly, beta prime is our new shape parameter for failures. We take our prior parameter beta and add the newly observed failures, denoted by F. Physically, this means every new success pulls the curve slightly to the right, and every new failure pulls it to the left, constantly refining our estimate. Now that we have our updating formulas, let us look at a real-world application. Imagine you launch a brand new website. Because it is new, you have absolutely no idea what percentage of visitors will buy. We are asked to find the updated posterior distribution and the new most likely conversion rate. We start with a flat prior distribution, setting alpha and beta to 1. On the first day, 10 people visit, 3 click buy, which are our successes, and 7 leave, which are our failures. We update the alpha parameter by adding the 3 new successes to our prior alpha of 1, giving us a new alpha of 4. Continuing with our website example, we must now update our failures. We take our prior beta parameter, which was 1, and add the 7 newly observed failures. This simple addition gives us our new beta parameter of 8. Our updated belief about the website's conversion rate is now mathematically represented by a brand new beta distribution with parameters 4 and 8. We have successfully transitioned from a state of total ignorance to an informed mathematical model just by observing 10 visitors. To finish our example, we need to find the new most likely conversion rate. We do this by calculating the mode of our updated distribution. We substitute our new parameters, 4 and 8, into the mode formula. Simplifying the numerator gives us 3 and the denominator simplifies to 10. Converting this fraction to a decimal gives us 0.30. The physical meaning of this final answer is that based on our initial blank slate plus the new data, the most likely conversion rate for our website is exactly 30%. We have covered a lot of ground today, so let us reinforce the most important ideas. First, the beta distribution is your go-to mathematical tool for modeling uncertainty when dealing with probabilities bounded between 0 and 1. Second, remember that its shape is entirely driven by alpha and beta, which simply represent your observed successes and failures. Finally, we saw how beta 1,1 represents total ignorance and how Bayesian updating allows us to seamlessly learn from new data by just adding counts together. You now understand the perfect mathematical framework for learning from experience. Great job!